Hey, welcome back to our series where we're really deep diving in the internals of JavaScript and in particular the V8 engine that powers the Chromium based browsers such as Chrome or Brave and of course Node.js itself. And we're really looking at the output of the JavaScript interpreter, and in V8 engine world that's called Ignition, to see what bytecode is generated that will eventually get optimized and compiled down into machine-specific code that will run on browser or in Node.js. But we are really deep diving to understand what's going on underneath. So where previously we looked at how the JavaScript engine works and we looked at how the accumulator works and what an accumulator is, we're now going to go a little bit deeper and then actually look at registers, which the accumulator needs to store the output of any arithmetic calculations for later usage. If you want to refresh what happened in that video, then a link will be appearing in the top right hand corner. But let's get back into it and deep dive into what a register is.
And what a register basically is a storage slot that is capable of storing a natural number. So essentially, it's a little bit like the accumulator, but it's just a bit of storage area, a little virtual register where you can store some values in. And one of the things I want you to think about is in your code, every declaration that you make, so whether it's a var, whether it's a let, whether it's a const, is essentially going to be stored in a register. So to bring that to life, what we're going to do is, rather than just returning a number 5, what we're going to do now is add the number 5 to an existing value in our function. So it's going to be a little bit more complicated, and we're going to have a couple of more arithmetic operations in there. So I'm going to go back to VS Code for a second. I'm going to go back to my example.js, and we're going to change this from being return 5, and we're going to call it add 5 now. So we'll just change this. So what we'll quickly do is we'll just clear the body of this function, and we'll set an initial value. So at the moment, I'm not going to pass any parameters in. I'm just going to set an initial value into a local variable. So I will create a const, and I'm going to call this const x, and we will set that initially to the number 10. So if we were trying to figure out what is going to happen in the bytecode, knowing what we know already, we could probably take a few reasonable guesses, right? So we saw this load SMI before, this load small integer, and we had this concept of the accumulator. We could probably figure that the number 10 is going to be loaded into the accumulator, right? And I just explained what registers are, so it probably isn't a massive leap to figure out that what we're going to try and do is take whatever number was in the accumulator and we're going to try and store it into a register that is representing X. And we'll see that coming up in a second. Now that we've got that in there, what we're going to do is we are going to return the value of X, and then we're going to do a little bit of addition. So we are just going to add the number 5 to that. So I'm not going to put 5 into a constant just now. I'm just going to return the number 5. So we'll hit the semicolon there. We'll save that. If we return to my terminal for a second and we run node example.js, we should be getting 15 returned, which we do. And then if we want to look at the bytecode, we can do that again. I just need to change the filter so it's not return 5 and it's going to be add 5 because that's the name of my function now. And we'll hit return. And it's returning a new set of bytecode. So again, we can see at the top there it's called add 5. If we look at this, we see the register count is now 1. Remember before we had 0 registers. Now we've got a register count of 1. So let's dig into that a little bit. And then let's have a look at the code underneath there. We see this load into the accumulator, LDA SMI 10. And you see that again, OC, which is load to accumulator, and 0A, which represents the number 10 in hexadecimal. So we guessed that correctly. So it's loading into the accumulator. And then we see this thing that's C6, right? So we've got a new opcode here, right, which is C6. And it says STAR0. Now, we introduced this concept of registers. So the R0, we could probably take a good guess that that's standing for register 0. And therefore, we could guess, in the same way as LD stood for load, we could guess that that stood for store. So, and we can guess that the A stands for accumulator. So let's bring that all together, and it's going to be store whatever's in the accumulator into register 0. So I took 10, I loaded that into the accumulator. So 10 is now in the accumulator, and then I'm going to store whatever's in the accumulator, which is 10, and we're going to put that into register 0. Cool. And then the next thing that happens here, the next command is add SMI 5, and I'm going to ignore this 0 for just now because it's a bit of an optimization, but we're going to ignore that for just now. So what does add SMI mean? Well, essentially the add is an operation, so we know that we do operations, mathematical operations with the accumulator. So it's a bit of a good clue. So it's going to add the small integer 5 to whatever is in the accumulator. So it's going to take this number 5 and put it onto the accumulator. Now the accumulator was 10 before. It's going to add that onto that, and then it's going to be 15, and then it will return that. So that's how that works. And again, if I wanted to simulate this on a piece of paper, I could. So again, what we're going to do is go back to the iPad, and we're going to draw out manually what's happening in the bytecode. So I'm going to need 3 columns. I'm going to need 1 column to represent instruction. And then I'm going to have a column to represent my accumulator again. And we're going to have a column now to represent R0. So it's going to be register 0, that virtual register that we have, okay? So the first thing that's going to happen is I'm going to put this begin. So begin isn't a real instruction, but I just want to show that my accumulator and my R0 is empty at this point in time. It doesn't have any values in it. And then the first instruction that I'm going to have is going to be this load small integer into the accumulator, this LDA SMI, and I'm going to load in the number 10. So let's put in LDA SMI and then 10. So it's going to load small integer 10 into the accumulator. So when that instruction runs, the accumulator is now going to be equal to 10. And register 0 doesn't have anything in it just now, so that's going to be empty. Now, the next thing that happens is, as I said before, every identifier, every declaration that you make in a function in JavaScript will have a representation mapped to a register. So I'll have a virtual register assigned to that. So in this case, because I was assigning the value 10 to my constant x, then x is going to map to R0. So what's going to happen is we're going to have a new instruction which is going to save whatever is in the accumulator, and we're going to save that into R0. So that is STA, so store whatever's in the accumulator, which is currently 10, and then put that into R0, register 0. So it's going to store whatever's in the accumulator into register 0. So at this point in time, the accumulator is still equal to 10. That doesn't change. But now in R0, we will also have the value 10, okay? So the next thing that we're going to do now is we're going to add the number 5 to whatever's in the accumulator. And how that happens is this add instruction. So it's add SMI and then the number 5. So what it's going to do is do an addition, so do an add, and it's going to add the number 5, which is a small integer, so add SMI 5, so it's going to add the number 5 to whatever is in the accumulator. So whenever I'm doing additions, multiplications, divisions, whenever I'm doing any sort of arithmetic, then that's going to be working directly on the accumulator. So essentially I'm going to load up the number 5 and I'm going to add it to whatever contents is in the accumulator today. So that will make the accumulator now equal 15. Now R0 is still going to be 10. I'm not changing register 0, only the accumulator is going to be 5. And then my final thing is I'm going to do a return, and it's going to return whatever's in the accumulator, which is currently 15. And that's the end of my function. Now, at the moment, you're probably thinking that's quite inefficient, right? I'm not doing anything with register 0. Although I've stored the value in there, I'm not returning anything. I'm not doing any calculations on it. So that probably seems quite inefficient. And that's kind of where the compilation phase and the optimization phases after the virtual machine bytecode occurs. So the The bytecode phase, the interpreter phase, is quite prescriptive. It does exactly what you were doing in your JavaScript. But then those other stages, such as the compilation phase or the optimize bytecode phases, that's the area where it would do some optimization and some caching and sort of get rid of duplicates to get a more optimized machine code that's going to run on browser. We're not going to worry about those optimizations because we're going to focus in on the bytecode at the moment, because that's, I think, what's going to help us become better JavaScript programmers. And in fact, if I just went back to our original diagram, that code, the journey that it's followed through for the add5 is we've done this parsing. It's created this abstract syntax tree. We've then went through the interpreter and it's produced that bytecode. So what you've seen there is what gets produced by Ignition. So this bytecode. And then, as I said, it's going to go through some optimization. So there's some optimization routines that run that make it a little bit faster, does caching, etc. And then eventually that bytecode that we've got here would then go into the compiler, which will generate the machine code, which will then run your program, whether it's on Node or whether it's in Chrome. So what we're going to do is store the number 10 into the accumulator, just like we did before. And then what we want to do is store the number 10 into R0. So we would just type in R0 equals accumulator there. So this is basically an equivalent JavaScript representation of what that bytecode is doing in the back end. And then finally, to do the addition, so I want to add 10 to 5. Every arithmetic that I do happens on the accumulator. So what I would do is type in something like accumulator plus equals 5. So that's essentially adding the number 5 to whatever's in the accumulator, and then I would return the accumulator. And that should, if I just change that to add 5, that would therefore should return 15. And if I just run node accumulator.js on my machine, you can see it returns 15. Now you're probably wondering to yourself, in my original example, why I just didn't do a return 10 plus 5. Why did I actually assign it to a constant, right? If everything occurs in the accumulator, why bother storing something in the register, right? In R0, why not just do a return 10 plus 5? And the answer is really simple. So if I just, as you see, I've just modified the code. And then if I come back and do, if I run my code again, you can see it's returning 15. But you see what it's now doing is doing LDA SMI 15, right? So what's actually occurring is it's done an optimization. So remember I said there was two phases. The first one is it would parse your JavaScript and create an abstract syntax tree, and then the second thing it would push it into the interpreter. Well, actually what's actually occurred there is an optimization's already occurred. It's either in the parsing or it's in the interpreter itself, I'm not quite sure, but it's smart enough to go, do you know what, you're just taking two numbers and adding them together, so all it's done is done the 10 plus 5 there. So I couldn't really demonstrate that without introducing the constant. That's why I sort of put that in there. So what we're going to do now is we're going to create a slightly more complicated example. So what we'll now do is, rather than just adding a number onto a constant, what we're going to do is add two numbers together. Again, I'm not going to use any parameters just yet. I'm just going to do this with local variables. So we'll create a new function. We'll call it add two numbers. As I said, no parameters at this stage. And I'm going to create a new variable called n1. It's going to be a constant, and we'll set that to the number 10. And then we'll create another constant. We'll call it n2, and it will be equal to 5. And then what I'm going to do is add these two numbers together and return the value. So we'll just type return n1 plus n2. And then finally what we'll do is just log the output. Yep. So if I just come back to my terminal for a second, and we type node example.js, you see it's returning number 15 as it did before. So let's have a look at the bytecode again. So it's now called add two numbers. We could probably guess, just before I return that, we could probably guess what's going to happen, right? Because some of this we've seen already. So you can sort of take a guess that we're going to have this LDA SMI 10. So it's going to load number 10 into the accumulator. It's probably going to do an STA R0, so store that 10 into register 0. we're probably then gonna load 5 into the accumulator again, and then store N2 into a new register called register 2, we would imagine. This is a bit of a guess. And then because we've got 5 already in the accumulator at this point, we probably need some sort of instruction in the accumulator which is going to be able to add whatever was in register 0 into the accumulator. And then that will give us a new value in the accumulator, and then hit return. In fact, we could probably draw that out on the iPad again, and actually let's take a guess before we actually do this. So if we go to the iPad, we type in instruction. We'll find out what the real instruction is in a second, but let's see if our guesses are good. So we'll have an instruction, we'll have the accumulator, and we will have R0, and we'll have R1, and we'll put that across there. So again, at the moment, we'll have this begin, although it's not a real value. We're just having that represented, and everything's going to be empty at that point. We're probably going to have this LDA SMI, and it's going to be 10, and so that will make the accumulator equal 10. R0 and R1 will be empty at that point. Then what will probably happen is we'll have an STA, and I've got to try and remember the syntax, and I think it was R0, yeah. And so therefore it's going to store whatever is in the accumulator into R0, so that will now equal 10. R1 will still remain empty, and the accumulator is still going to be 10 at this point. Then I would imagine there's going to be another LDA SMI, and it should be 5. And so that should make the accumulator equal to 5 now. R0 is still going to be 10. And R1 should still be empty at this point because we haven't done anything with it. And then we will STA R1. So 5 is in the accumulator still. R0 will still be 10. And then what will happen is 5 will be stored in R1. And then we're going to have some sort of magic command, some sort of add. And I would hope that it's going to add whatever is in R0 to the accumulator, right? That's really what I want to do. So some sort of add, I would imagine R0, and that would hopefully make the accumulator equal to 15, and that would still be 10, and that would still be 5. And then I would expect a return, and that will therefore return the 15 in the accumulator. That's what I expect to happen. Let's go to our machine and see actually what happens. So we've created a function. Let's run the bytecode for a second. So I'm getting 15 coming back, so that's a good sign. Let's have a look at the actual bytecode. Yeah. Okay, so we're getting the number 15 coming back, which is good. So it's the right value at least. Let's look at the top there. Good news is register count is now equal to 2. So we know we have 2 registers now. So R0 and R1 do exist, so that's goodness. Let's have a look at the instructions that have been created. So we have an LDA SMI 10, so that was good. Our guess was good. And then it's star 0. So good news, we got that right as well. So 10 is now in the accumulator, and 10 is in register 0. And yep, we were correct. LDA SMI 5, so it's loaded 5 into the accumulator. And yep, it's done a STA R1, so it's now stored that 5 into register 1. So our guesses were correct. And then interestingly enough, so we were slightly wrong here. What it's done at the moment is then it's done a load. So it's loading whatever is in R1 back into the accumulator. Okay, that's fine. So R1 is going to have 5, so it's just loading 5 back into the accumulator. Fine, okay, it's logically the same. And then what it's doing is adding R0 to whatever is in the accumulator. So yeah, it's a little bit more precise. than we were. So it's added that instruction, which is LDR R1, in between the storing of the value into the accumulator, but essentially everything else is the same. So the key thing is there are sort of two new commands that are introduced at this point. So LDAR, which is load into the accumulator the contents of a register. So LDAR R1, so load into the accumulator the contents of register 1. And then, so we know what that does. So in this case, it's loaded 5, which was in register 1, into the accumulator, which is fine. And then obviously we have a new command also, which is add. So, and what add does is add R0, so add whatever's in register 0 into the accumulator. So at that point, R1 had 5 in the accumulator. We've added the 10 from R0, the accumulator, sticks them together, and we now have the number 15, and then 15 is returned at the end as normal. Again, if we really wanted to simulate this in JavaScript, we could. So let's just bring up my VS Code for a second. We'll select the accumulator code. What's actually happening is now I have two registers. I have R0 and R1, so we'll add a new register. So we now have accumulator, R0 and R1, which is cool. Accumulator was set to 10. Then R0 is equal to accumulator, so that doesn't change. And now what we're going to do is put accumulator equals 5, and then we're going to set R1 equal to accumulator. Now, as we said before, it did this kind of weird step where it loaded into the accumulator whatever was in R1, so we just do that again, so it's been very precise. So accumulator is equal to R1. And then finally, what we're going to do is add to the accumulator whatever is in R0. So that's accumulator plus equal R0. And then we'll return the value of the accumulator. So let's just run through that again. So accumulator is going to be 10. We're going to store 10 in R0. Then we're going to load 5 into accumulator and then store that in R1. So R0 is going to be 10. R1 is going to be 5. Then we're going to load whatever's in R1, which is currently 5, back into the accumulator. So accumulator is 5. And then we're going to add the contents of register 0 on top of whatever's in the accumulator. So 5 is in the accumulator just now, and we're going to perform a function to add whatever's in R0, which is 10. So that will therefore become 15. And then 15 will be returned from the accumulator. And if I were just to go back to my terminal and run node accumulator dot JS, you'll see it's returning 15. So if that helps, I don't know if that helps people by being able to express what's going on in the back end of JavaScript, because that's the coding language but hopefully this is starting to make sense. Now, what you can imagine is, because I said before it's a set of virtual registers, and every declaration that you make, every identifier you create, so whether it's a let, a const, a var, whatever, it's got to have a corresponding register. You can imagine, as I just keep adding things to my code, those registers are going to keep getting mapped. So if I went back into VS Code, so as I said before, every declaration that you make in a function, whether it's a const, a var, a let, doesn't matter, every declaration you make is going to be mapped to a register of some sort, and that needs to be declared up front. So no matter what I do in this function, as I start adding new constant declarations there, then you're going to see the number of virtual registers increase. So I could just add a few values. So let's put that equals 17, and then I could put n4 equals 20. I won't add them together, but if I was just to then go back into my code and then run example.js again, what you're going to see is my register count is mapping that. So I've got 4 registers now, and you can sort of follow the code: 10, 5, 17, 20, and you can see register 0, 1, 2, 3. So we've got this sort of direct mapping between the constant and let declarations that I would make with the number of virtual registers that I've got in my machine code. And of course, because I'm not doing anything with N3 or N4, I would expect the optimizer to sort of do some optimizations when it produces machine code, because there's no calculations happening there. But, from the bytecode perspective, it's been really, really precise.
All right, so by now we should have a pretty good idea of how the accumulator works and how the JavaScript engine works in general and how it produces bytecode out of the JavaScript source code that you create. And in the next video, we're going to deep dive even further into the accumulator and some of the mathematical operations that you can run. So far we've only looked at additions, and in the next video we're going to look at multiplications, divisions, subtractions, etc. All right, I'll speak to you in the next video.